Okay, I think I have this set up so that it is recording. That's the part I always forget. Okay, I believe we have a test in our next class meeting. We'll let the test go for the whole hour and 20 minutes. So if you finish early enough, you can leave. We won't do anything after the test. That sound okay to you? I put a review sheet on the Blackboard yesterday, so I don't know if any of you even got a chance to look at it. So I'll talk briefly about what's going to be on the test, but before I do that, maybe I should ask if you have any web work questions that you'd like to go over. Yes, sir?
It's finding absolute extremely for a function on the interval.
Okay.
It's f(x) equals sin x minus cos x on 0 to pi.
Do you know which number this is?
4, I think.
Okay, so we're starting with web work. And the question is, for this particular function, find the absolute max and the absolute min. So we're guaranteed that every continuous function defined on a closed interval has both an absolute maximum and an absolute minimum. What makes you think this is a continuous function? Yeah, sines and cosines individually are continuous, and so the difference of them is also continuous. Okay, so our candidates for the absolute max and min would occur either at the endpoints or at critical numbers within the interval. So we'll take the derivative and see how many critical numbers we can find between 0 and pi. When you take the derivative of the sine of x, you get a cosine of x. Derivative of cosine is minus the sine. So do you agree that the derivative is cosine of x plus the sine of x? So we set the derivative equal to 0. And so we are looking for values of x at which the cosine and the sine are the same, but have opposite sign. S-I-G-N, sign. Can you tell me a reference angle at which the cosine and the sine are the same? Pi over 4. Now, in which quadrants would they have opposite sign? 2 and 4. So using pi over 4 as your reference angle, which version of pi over 4 is in quadrant 2? 3 pi over 4. And now which one is in quadrant 4? Got it. Now 7 pi over 4 is not in the prescribed interval. You have to keep only the ones between 0 and pi. So let's go ahead and toss that one. And what we have to do next is plug the endpoints and that one critical number back into F and see which one of those values is the largest. So I'm going to find F of 0, F of 3 pi over 4, and F of pi. So I usually do this in table form. I'll just do it like this today. So I'm going back up here. F of 0 is the sine of 0 minus the cosine of 0. Sine of 0 is 0. Cosine of 0 is 1. So we get 0 minus 1 is a negative 1. Oops, I just wrote that in the wrong line. All right, let's put 0 here. Let's put F of 3 pi over 4 here. We need the sine of 3 pi over 4 minus the cosine of 3 pi over 4. Now in the second quadrant, sine is a positive number. Sine of 3 pi over 4 is square root of 2 over 2. So is the cosine of 3 pi over 4, but in quadrant 2 the cosine is a negative square root of 2 over 2. So we have square root of 2 over 2 minus a negative square root of 2 over 2. So I get 2 of those, which cancels with the 2 on the bottom, and that leaves us a positive square root of 2. Then F of pi is the sine of pi minus the cosine of pi. Does anybody know the value of the sine of pi? 0. Cosine of pi? Negative 1. So we've only got one negative number. That makes that clearly the absolute min. Which is larger, square root of 2 or 1? Square root of 2 is 1.14-ish or something like that, 1.41. So this number here is the absolute max. That work for you? Got another one? Anything else from that work?
I have a question, nothing over, please tell you another question. If you have a function that's not continuous at a certain x value, and it's the x value is in the interval, how would you answer that? If it's asking for absolute between.
Well, you're not guaranteed any. If it's not defined at that point, then it's probably a vertical asymptote, which means the graph is either going to plus infinity or minus infinity. And so you would not have a max if it's going to plus infinity, or a min if it's going to minus infinity. Now, if it's got a critical number somewhere else, it's possible that it's a larger value, but you're just not guaranteed. So the best way to answer the question is maybe to graph it. One of the examples was a piecewise defined function, where there were no critical numbers in the interval, but there's a sharp corner where the two pieces meet. And so if you looked at the graph, you can answer the question that they're at the sharp corner you have them in. What else do I have to tell you about web work? Nothing? Well, then let me see what I can tell you about your task. Let's kind of outline it. It'll be formatted like the last one. Bring some paper so that you can write your answers on notebook paper, and I'll print your test on a single sheet of paper. For your test on Tuesday, let's see, I believe this is open. I'll get to my Zoom meeting. I guess I don't. I hope my Zoom meeting's taping. For your test on Tuesday, we started with derivatives of trig functions, exponential functions, and log functions, and those were the basic derivatives. You'll probably see more of them with the chain rule type combination problems. But for instance, so maybe I'll ask you something like find an equation of the tangent line to f of x is equal to 4e to the x times the sine of x. Should put something else in here. Plus the secant of x at the point where x is equal to 0. That was the problem on the test. Did you get that one right? Come on, I want to see some confidence here. Yes, I can get that one right. Easy schmeezy, correct? You're going to take a derivative. Then you're going to need to know where what the value of the derivative is if x is equal to 0, and that's the slope of your tangent line. Then you're going to need your y1 value that goes with x is 0. So you find that by finding f of 0. And then you plug it in the point slope formula, and you're done. So let's do it. Take the derivative of that thing. Let's see if we can all agree what the value of it is when x is equal to 0. Nice whole number as your slope. Anybody want to tell me what they are for their slope? Hold up your fingers. That's correct. 4 is your slope. Yep. So we've got a product rule action going on here. So when I take the product rule on that bit, here's the first times the derivative of the second plus the second times the derivative of the first. Derivative of e to the x is e to the x. Derivative of sine of x is cosine of x. And now I'm going down here and taking the derivative of the secant. Did you remember that derivative?
X
Nope.
or
Secant x tan x. Now we're going to plug 0 in for each x. E to the 0 is going to be 1. Cosine of 0 is going to be 1. But sine of 0 is going to be 0. Secant of 0 is the same as the cosine of 0. That's 1. Tangent of 0 is 0 because it's sine divided by cosine. So we've got 4 times 1 times 1 plus 4 times 1 times 0 plus 1 times 0. And that's what gives us a slope of 4. Now we need our y1 value. So we go plug 0 into our original function. 4e to the 0 sine of 0 plus the secant of 0. Again, the sine of 0 is 0, so that knocks that out. Secant of 0 is 1, so f of 0 is 1. And then the point slope form is y minus y1 is equal to m times x minus x1. We found y1 to be 1, and m is 4. So there's the equation of our tangent line. You can put it in whatever form you want. That will work for me. But again, most of the stuff that we do from that section will be in the chain rule part. I'll ask you chain rule problems. So in the next section, in section 3.4, we had that stuff with our motion problems. And that the given function is the position at time t. Its derivative is the velocity at time t. And its second derivative, or the derivative of the velocity, is the acceleration at time t. A positive velocity means the object is advancing or going up if we're throwing an object in the air. A negative velocity means the object is retreating or falling down. Acceleration positive means it's speeding up. Acceleration negative is it's decelerating, slowing down. And then speaking of speed, speed is the absolute value of the velocity. I've got a nice one that we can learn. So let's assume that the position of a particle moving along a number line is given by S of t is equal to 4t cubed minus 2t squared plus 5 for t in the interval from 0 to, let's go just to 3. Find the velocity at any time t, the acceleration at any time t, times at which the object is stopped, and let's find intervals on which the object is retreating, and let's find intervals on which the object is advancing, and then, it doesn't fit on my page here, we'll find the total distance traveled. So you can get the velocity and acceleration before you can even write the problem down. Put a bigger number than that. Can we change that 2 in front of the t squared to a 12? Just slip a 1 in there. That way maybe your numbers are better. Slip a 1 right here. I'm not doing that for you. I'm doing that for me. I don't want to have to plug in goofy fractions. So 4t cubed minus 12t squared plus 5. So assume you've got the velocity and acceleration already. How do you know when the object is stopped? Set the velocity equal to 0. And hopefully that little change I made making it 12 gave you a better value of t. So you got as its velocity, the first derivative, 12t squared minus 24t, and acceleration is the second derivative, so we'll get 24t minus 24. The times at which the object is stopped, we set this velocity equal to 0. And we'll solve that by factoring. We have a common factor of 12t. That leaves the other factor as t minus 2. Now set each factor equal to 0. 12t is 0 when t is equal to 0. T minus 2 is equal to 0 when t is 2. T is equal to 0 is the endpoint, so we don't really need that. T is equal to 2 is in our time interval, so we keep it. Now we can figure out intervals in which the object is retreating and advancing by looking at the sign of which of these? The sign of the velocity. So let's make a number line from 0 to 3, put the 2 in there since it's stopped, and get the sign of the velocity in those intervals. I'll look at it in factored form. If I use 1 as a test point, I have 12 times a negative 1, that's going to give me a negative velocity. If I use 2.5 as a test point, my first factor is positive, and so is the second one. So it's retreating on the interval from 0 to 2. So, oh, by the way, it's advancing on the interval from 2 to 3. At 3, I probably should put a square bracket, and at 0, there's no velocity, so we should use the square bracket on 3. So that answers both of those questions. All right, now let's get the total distance traveled. So it does something between 0 and 2, it's retreating, and then between 2 and 3, it's advancing. So let's find the distance that it travels in each of those time intervals. So we need the difference between s of 0 and s of, what was that time number 2? That's where it's retreating. And then add to it the difference between s of 2 and s of end point is 3. I put them in absolute value bars because I don't know which one's which one's bigger. So we got to go back to the original function. So remember that s of t is 4t cubed minus 12t squared plus 5. And so when s is 0, and when t is 0, s is 5. When t is 2, let me do that up here. I have 4 times 2 cubed minus 12 times 2 squared plus 5. 2 cubed is 8. 4 times 8 is 32. 4 times 12 gives me minus 48, and then plus 5. So the 32 plus 5 is 37. Minus 48 is a negative 11. Hopefully. Now I put that negative 11 here. And now let's find s of 3. S of 3 is 4 times 3 cubed is 27, minus 12 times 9 plus 5. 4 times 27 is 108. Let's see, 10 times 9 is 90, 2 times 9 is 18, so 9 times 12 is also 108. That means s of 3 is 5. So our diagram looks like this. At time 0, it's here on the number line at 5. Then at time 2, it backs up all the way to the coordinate at negative 11. And then it's going to turn around and go all the way back to 5. So it goes backwards 16 units, and it goes forward 16 units. And that's what these numbers show. So 16 plus 16 is 32 total units traveled. Okay. So now let's look at one of the other motion type problems. If you stand on a cliff that is 80 feet high and throw a rock with an initial velocity of 64 feet per second, then a formula for the height of the rock at any time t is that's your first task. Do you know it? If you neglect anything other than the effect of gravity acting on the rock, no air resistance, anything like that. Good. So this is what she said. Negative 1/2 g t squared plus the initial velocity times t plus h0, the initial height. When we're in units of feet and seconds, what do we use for g? 32. What are we going to use for v0? 64. And h0 would then be the 80. So let's fill all that in. So we can go ahead and multiply the half with the 32 and get negative 16t squared plus 64t plus 80. So if we know its position at any time t, then some of the burning questions that are eating at us are, how high does the rock go? When does it hit the ground? What's its velocity when it hits the ground? So I want to see if you can answer those three questions. How high does the rock go? When does it hit the ground? What is its velocity when it hits the ground? He's going to talk us through the steps we take to figure out how high the rock goes. Where's the rock go? The picture tells you, right? The picture would be something like this. You're up here 80 feet. You're going to throw this rock, and it's going to land. You set velocity equal to 0. So find your velocity and find when it's 0, and then you find the height at that time. Find where the velocity is 0, and then plug it into your height function. Check up with you. Velocity is the first derivative of the height, whether I call it S or H, who cares. So negative 32t plus 64. Velocity is 0 when 32t is equal to 64, and so that's at t is 2. Then we need the height at t is 2. H of 2 is negative 16 times 2 squared plus 64 times 2 plus 80. 4 times negative 16 is a negative 64. 2 times 64 is 128. So negative 64 plus 128 is 64. 64 plus 80 is 144 feet. Anybody get that number? All right, next part. When does it hit the ground? How do you find that time? Height is 0. Set the height function equal to 0. Hits the ground when the height is equal to 0. So maybe I've given you something that you can factor. Let's see, does 16 go into 80? How many times?
5.
So let's pull out a negative 16. 16 divides all three of those numbers. Pull out a negative 16. So we're pulling out a negative. That's going to change the signs. So by gosh, I did give you something that factors. I need factors of 5, opposite in sign, that adds a negative 4. 5 and 1, right? There's only 2 factors of 5. Opposite in sign, I'm going to need a minus 5 and a plus 1. So when I set each factor equal to 0, I get t is -1 and t is equal to 5. -1 makes no physical sense. 5 has to be positive. So it hits the ground in 5 seconds. So the velocity when it hits the ground should be a negative number. Let's go to our velocity function. That was the -32t plus 64. And we want to know that value when t is 5. What is that? -96 feet per second. If I ask for the speed would be positive 96 feet per second. Speed is the absolute value of velocity. I won't ask you both of those. Which do you prefer? The number line deal or the...
All of the ones.
Which one?
Yeah, just do them all.
You want to do them all?
Yeah.
Okay, I'll let you write the test. Okay, then there's the chain rule. So if there's anything that you need to emphasize for this test, my gosh, it's the chain rule. Because it shows up all through Calculus 2. I've got a couple of students who are just struggling to learn Calculus 2 because they never fully mastered the chain rule. Calculus 2, we got to work backwards from derivatives. Right? We got to do some integration by substitution. And these couple of students just have so much trouble because they didn't master the chain rule. So don't be that student next semester. You guys rock on this chain rule thing. Okay? So let's do a couple of examples taking the derivatives using the chain rule. Does any of this help you, or is this too redundant? Do I need to... You like it? So that's in section 3.5 is the chain rule. So I want you to master this. Okay, so let's find f prime of x. And my first one, let's let f of x be x squared time over x squared plus 4 all cubed. Simplifying is not a big deal for me on the test, but I'll practice simplifying with you today. So if you want to take a stab at simplifying your derivative, go right ahead, but remember on the test I won't make you do that. Should make you do that, huh? But then I have to look at what you've done. And that burns my eyeballs. It's too late to invent algebra. It's already been invented. You stick with the conventions of algebra and don't make your own. Simplify things, that doesn't mean multiplying them out. It pretty much means factoring and canceling. you start simplifying, let me make sure you've all got the correct derivative. We're doing the quotient rule. So we can do the bottom times the derivative of the top minus the top times the derivative of the bottom divided by the bottom squared. So I'll do it right over here. Here's the bottom factor, and the derivative of the top is 2x. Here's the top factor. Now the bottom is where we do the chain rule. We've got a quantity to third power. So you bring the power down, raise the quantity to one power less, multiply by the derivative of what's inside. So we'll have 3 times x squared plus 4 squared. The derivative inside gives me another factor of 2x. All over the bottom squared. Everybody happy with that part? Okay, now to simplify this, let's worry about the bottom first. I have something cubed squared. Does that add up to the 5th power or the 6th power? It's the 6th power. Raise the power to a power, you multiply exponents. So on the bottom you can put x squared plus 4 to the 6th. On the top, I'm going to rearrange terms first. I'm going to write the 2x in front, and then the x squared plus 4 cubed. And for this next term, I'm going to put all these little dangling terms together, the ones that aren't in the quantity squared. X squared times 3 times 2x will give me a 6x cubed, and that's behind the minus sign. And then I've got the x squared plus 4 squared. When you write it like that, you can see there's a common factor of x squared plus 4. What's the most that's in common? 2. So I want you to knock out a factor of x squared plus 4 squared from all 3 spots. I can take both of these out. Take 2 of them away from here, leaves me a 1st power. Take 2 of them away from here, leaves me a 4th power. And so now we have 2x times x squared plus 4 to the 1st minus 6x cubed all over x squared plus 4 to the 4th. Now you simplify the numerator by multiplying it out. Distribute the 2x here and you get 2x cubed plus 8x minus 6x cubed. And then you can combine the 2x cubed with the 6x cubed and get a minus 4x cubed. You could leave it there. You could pull out the common factor 4x. That doesn't matter. But we've got it in a nice simplified enough form so that if you wanted to do a second derivative, you could. Right? Yes, sir.
On the test, where would it be fine for the
Yeah, right here. This big old messy thing right here you can do on the test. If you want to try to simplify, it won't take off points unless you do something really hideous. But I usually just look to here. Questions on that one? Okay, let's do another one here. Let's take the derivative of, find f prime of x for number 2. Come down. F of x is equal to the sine squared of the square root of x. Find the derivative of that. remembering that if the square is next to the trig function, that means the entire trig function is squared. That's the same thing as saying this. And so when you take the derivative, you start out here and use the power rule. Bring the power down, raise it to 1 power less, and then multiply by the derivative of what's inside. The square doesn't affect the angle, so that's not the square root of x squared. The sine of the square root of x is squared. It's easy enough to see that here. Yeah, that's pretty good. That's pretty good. Bring the power down, raise it to 1 power less. Multiply by the derivative of what's inside. What's inside is a sine. Derivative of a sine is a cosine. And the very last thing you take the derivative of is the angle. Right? So your derivative should look something like this. 2 times the sine of the square root of x to the first. Then we get the cosine of the square root of x. Then the derivative of the square root of x. Can you make that jump right there, or do you always write it as a power and then take the derivative? Okay, remembering that the derivative of the square root of x is 1 over 2 square root of x. The 2's will cancel, and so you can write sine of square root of x over cosine square root of x divided by the square root of x. If you want to do a trig identity, you can. I knew somebody would do that. That's a double angle formula for which trig function? Sine of 2x. So this would be, you can use the trig identity and say that's the sine of 2 times the square root of x. I won't. I'll cancel here. Okay, the next one I want you to find the second derivative of f of x is equal to the tangent of e to the 3x. Second derivative of the tangent of e to the 3x. Clock has a mind of its own. I'll tell you what. It's hard to keep you guys under control. You're just laughing and rolling in your eyes, having so much fun. I think there might be a keg somewhere in here. You don't keg a root, do you? What's the derivative of the tangent? Secant squared. So your first derivative will be the secant squared of e to the 3x times more 3 e to the 3x. Right? F prime of x, derivative tangent is the secant squared of the same angle. Now we take the derivative of the angle. The derivative of e to the 3x is itself times the derivative of the power. So with that in mind, what's your plan for the second derivative? Product rule. We've got a first term and a second term. So you're going to do the first times the derivative of the second plus the second times the derivative of the first. I'll give you 10 minutes to do it. Oh, time's up. 10 minutes to do the product rule. Good gosh. I'll do the product rule for 10 minutes. All right. See you right with your feet. That does sound like a bad idea. You're an artist. Yeah, there was that guy that was in that movie.
Oh, in that movie.
In that movie. That'd be real one if it's in a movie. All right, your 10 minutes are up. The first term is the secant squared of e to the 3x. The derivative of your second term is itself times the derivative of the power. The derivative of power spits out another 3, so I'm going to get a 9 e to the 3x. Then the other way around, to take the derivative of the secant squared, we have to do it the way we did the derivative of the sine squared. That's the secant of e to the 3x quantity squared. So, will I be able to fit it in here? I doubt it. We'll bring the power down, raise it to 1 power less, and then multiply by the derivative of what's inside. So I'm thinking of that as the secant of 3 e to the 3x quantity squared. So there's the power down, there's e to the 3x, the first power. Now in here, I take the derivative of the secant. What's the derivative of a secant? Secant of the angle times the tangent of the angle. So this is going to be the secant of e to the 3x times the tangent of e to the 3x. Next, what comes next? E to the 3x times 3. And then I close it up. So all of this fits right in here. We ain't simplifying that. No matter how much you make me, I'm not simplifying.
It's not hard.
Not hard?
No.
Okay, then I guess no matter how much you make me, I'll simplify it. All right, so I'm going to put the 9e to the 3x in the front. Secant squared e to the 3x here. Let's see. I'm going to write this first. I'm going to write it the way I see it. 3e to the 3x. 2. I've got a secant of e to the 3x times another secant of e to the 3x. So that'll be 2 secant squared e to the 3x times a tangent e to the 3x. And then I'm going to take this 3e to the 3x and multiply with that 3e to the 3x and get 3 times 3 is 9. 3 plus 3 is 6. I don't want to simplify it anymore. That's not worth it. Life's too short. See? All right. Now what I want you to do is find where this tangent line is horizontal. Find where the tangent line to, let me find the nice one. F of x is equal to 6x squared times e to the 1 minus 3x. Find where the tangent line to the graph is horizontal. So what you got to do? And not only find the derivative, find where the derivative is equal to 0. Find where the derivative is equal to 0. Using the product rule, correct? Let's check if you got this. So here's the first times the derivative of the second itself times the derivative upstairs is going to give me a -3 plus the second times the derivative of the first is just 12x. So I'll put this -3 with the 6x squared and get a -18x squared. E to the 1 minus 3x. And then the other one is 12x e to the 1 minus 3x. I'm going to factor that. I've got a common factor of 6, of x, and e to the 1 minus 3x. So I'm going to pull out 6x e to the 1 minus 3x. And I'm left with a -3x plus 2. So I set my three factors equal to 0. 6x is 0, e to the 1 minus 3x is 0, and -3x plus 2 is 0. 6x is 0 only when x is 0. This is never 0. This is always positive. And this is where 3x is equal to 2, so I get x is 2/3. So there are two places where the tangent line is horizontal. Did you get those? Good. Good. Okay, so let's move on to section 3.6, which was implicit differentiation. Given an equation, find the derivative of the function using implicit differentiation. Also in this section, we had the derivative formulas for the inverse trig functions. We had the derivative formula for a number other than e to the x. We had the derivative formula for logs of other bases. And then we had the logarithmic differentiation to take derivatives of a function of x to the x. And we had higher order derivatives using implicit differentiation. So I can ask you a lot from here, like, for instance, let's see, what page am I on? I got to try to number my pages here. And number 4. And number 4 right there. All right, so here's page 5. And we're looking at section 3.5, implicit differentiation. So let's see if you can find dy dx in terms of x and y if, oh, let's see, 4y squared plus 3 natural log of x plus 2 I don't know, sine of x times y to the 5th is equal to 10. So you got an equation, x's and y's are mixed up. Implicit differentiation allows you to take the derivative of the equation term by term. And just remember, anytime you take the derivative of a y, it's a function of x, so you tack on your y prime term, which I wrote in this case is dy dx. Feel free to write y prime if you would like instead of dy dx. Start solving for dy dx. Let me make sure you got this first line correct. The derivative of 4y squared is 8y to the first power times our y prime term. So far so good? Boom. Derivative of 3 natural log of x is 3 times 1 over x, or just 3 over x. Here I got to do the product rule, so I'm going to call that the first term. And there's our second term. So I've got the first times the derivative of the second. Just like in the front, we take the derivative like we normally would, but then tack on a y prime. Now the second times the derivative of the first. Derivative of 2 sine of x is 2 cosine of x. And then finally the derivative of 10 is 0. Is that line okay with everybody? We have 2 terms that have a y prime on them. We're going to keep them on the left-hand side. I'm going to subtract 3 over x from both sides. And I'm going to subtract that last term from both sides. So we're going to keep the 8y y prime plus 2. Let's go ahead and multiply the 2 with the 5 and get a 10. 10 sine of x, y to the 4th, y prime. Then I said I'm moving over the 3 over x. Then I'm moving this whole term over, so minus y to the 5th times 2 cosine of x. We kept these together so that we can pull out the common factor of y prime. I don't care about the other common factors. I'm trying to solve for y prime. So we pull the y prime out of here, and that leaves me an 8y plus 10 sine of x, y to the 4th in the parentheses. Recopy the right-hand side down. And then the last step is to divide by what we have right here. So we have y prime is minus 3 over x minus y to the 5th times 2 cosine of x divided by all of this other stuff. 8y plus 10 sine of x, y to the 4th. Maybe I jumped in too soon. Do you think you were able to get all the way down to there? Seen those steps before? Done those steps before? Oh, boring. All right, let's find a second derivative. Let's go with find y double prime in terms of x and y if you have, I don't know, 6x cubed minus cosine of y squared is equal to the square root of pi. X cubed minus the cosine of y squared is the square root of pi. And you know you start the same way. You first get y prime in terms of the x and y. Then you start from there and take the derivative of both sides to get y double prime. make sure you got the first derivative correctly. Take the derivative term by term to get 18x squared. Derivative of cosine is minus a sign, so this becomes a plus. The sine of y squared. Move inside and take the derivative of the angle, and you get 2y prime. What'd you get as the derivative of the square root of pi? Good. Okay, then you're going to solve that for y prime. So you're going to first move this term over, and so you'll have the sine of y squared. I'm going to put the 2y in front, the y prime here, minus 18x squared moved over. Then we divide by the 2y sine of y squared, so y prime is negative 18x squared over 2y sine of y squared. Did anybody reduce that and made that a negative 9 and cancel the 2? Or did you leave it there? Or did you even get that? You did not reduce it? Okay, then let's take the second derivative from that step. Right, there's y prime. The derivative on the left is going to give you the y double prime. The derivative on the right involves the quotient rule, but it'll also involve the product rule when it comes time to take the derivative of the denominator. Okay, so I'm going to write that. We've got y double prime is equal to the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. This is the step that has the product rule. Because you got two terms down there. So I'll give you a minute to try that while I find another piece of paper. There's one. To save some time, don't simplify your second derivative very much. It's a mess. All right, I want to play. Oh, who knows? I just make this stuff up. All right, bottom times the derivative of the top. There's the bottom. The derivative of the top is just a negative 36x. So I don't see where things are messy. That's pretty clean. Now the other way, minus the top. So minus a minus is going to give me plus 18x squared. And in here we're going to do the product rule. We've got the first times the derivative of the second. Derivative sine of y squared is cosine of y squared times another 2y times y prime. We're at, right? That's half of it. The other half is, where am I? Sine of y squared times the derivative of 2y is 2 times y prime again. And then all of that over the bottom squared. I want my derivative only in terms of x and y. So everywhere I have a y prime, we're going to put in the 18 over x squared 2y sine of y squared. So my final answer will look something like, I'm going to go ahead and put these together. 2 times negative 36 is a 72 xy sine of y squared. I'm going to keep that as a plus 18x squared out front. I'm not going to take anything out. I guess I should, huh? Yeah, let's factor out a y prime. Let's factor that out. So here I'm going to have 4y squared cosine of y squared. And here I'm going to have 2 sine of y squared. Then I'm factoring out the y prime right here. But y prime from the previous step was negative 18x squared 2y sine of y squared. All divided by, square this is 4y squared sine squared y squared. Yeah, that is a mess. But I did have to factor that out, so thank you.
I wonder what that graph looks like.
I don't. There's a bunch of holes in it. There's a hole when y is 0. There's a hole when y is 0 pi, 2 pi. Okay, so here's another one. Find f prime of x if f of x is the natural log of the arc sine of 4x. So sneak in my inverse trig functions. We have derivative rules for those. It's also the chain rule for the logarithm. The derivative of the log of u is 1 over u times u prime. So you've got to remember the derivative formula for the arc sine. Derivative of the natural log of u is 1 over u times u prime, and the derivative with respect to x of the arc sine of u. Who's going to tell me the formula for the derivative of the arc sine of u? Okay. I wrote it like that in class, but you can squeeze that u prime on top. You're going to use both of those when you find the derivative here. So don't worry about simplifying. Let's just knock this bad boy out.
So, f prime of x, this part is the u right now. Derivative of the natural log of u is 1 over u times u prime. So now we're taking the derivative of the arc sine of something else. We get 1 over the square root of 1 minus the something else squared. Then we go inside these parentheses and take the derivative and get a 4. So something like that. You can write that 4x all squared as 16x squared. You can put that 4 on top of that. Is that okay with y'all? All right, next. Find f prime of x if f of x is equal to, how about the cosecant of x all raised to the 5x power.
Does that make you think of what you're going to do? It's not a 5 up there, it's a 5x. The base is a function of x. So when both the base and the exponent are functions of x, tell me what to do.
Give up.
Give up?
I think we defined u as what we're doing right. And it was du times ln u times u prime.
That's only if the base is a constant.
Take it out.
We've got a function of x raised to a function of x power.
You take the ln of
That's right. Remember, when you have a function of x down here, and the power is also a function of x, you start by taking the natural log of both sides. Because that'll allow us to bring the power down. So you might want to start by calling this thing y. And then you're going to take the natural log of both sides. And that brings the 5x down in front. And then from here, it's an implicit differentiation problem. Take the derivative of both sides and solve for y prime. What's the derivative of a cosecant? Spot you a minus sign. Not going to tell me? Derivative of cosecant is? Negative cosecant of x cotangent of x. Don't forget the product rule on the right-hand side. Oh, I'm doing too much of this stuff. All right, the derivative on the left-hand side is 1 over y times y prime, correct? The derivative on the right is with the product rule. So we have the first times the derivative of the second. The second is a logarithm. We saw a second ago the derivative log of something is 1 over that stuff. Now times the derivative of the cosecant of x, which we said was negative cosecant of x cotangent of x. So we're halfway through there. Now the other part of the product rule is the derivative of the first one times the second. And conveniently enough, one of those cosecants cancels. So I can write my first term as minus 5x cotangent of x plus 5 natural log of the cosecant of x. Then I'm going to solve for y prime by multiplying both sides by y. So you can leave your answer there, or if you want, you can put your y back in, which was the cosecant of x, all raised to the 5x. Can you do something like that? Yes, you can. Yes, you will. On Tuesday, you will. We'll do something like that. I'll put one of those on there. All right, so there was a whole bunch of stuff there in that section. And the other derivative rule that you mentioned was for something like this. Let me show you the difference. Find f prime of x if f of x is equal to, say, 10 raised to the 1 over x. See, this time the base is a constant. So we don't have to do all that logarithm stuff. You can. If you forget the derivative rule, you can. You can do the same steps to this one that you did to the last one. Or you can use the formula for the derivative of any number to a power is itself times the natural log of the base times the derivative of the power. So here the base is 10. So according to this, the derivative of 10 to the 1 over x is 10 to the 1 over x times the natural log of 10 times the derivative of 1 over x. If you forget that derivative rule, just do the same steps you did in the last problem. You'll get the same answer. What's the derivative of 1 over x? There you go. So section 3.5 had a whole bunch of stuff in it. What was in section 3.6? Is that related rates? That was 3.6? What was in 3.6?
What we just did was 3.6.
And what was in 3.5? 3.5 was the chain rule? So I labeled it wrong. Good, then I'm further along than I thought. Now we're in 3.7, 3 related rates. What kind do you like? The fun kind. Okay. Okay, what's a fun kind? Let's see. This is you. You are 200 yards, which is probably way too close, to a rocket. And this rocket is lifting off. And it's raising at a rate of How fast can a rocket go?
Very.
I don't know.
Very few percent.
Let's make this a nice number. Let's make this 300 yards. I want to make a 3, 4, 5 triangle. So that's 300 yards. This is raising at a rate of, I really don't know a good speed.
It'd be like miles per millisecond. It'd be
Okay, well, I'm in yards. I don't want to put you 300 miles away.
Just make some.
All right, this is 3 miles. You're 3 miles away from the rocket. You got good eyes? Can you see 3 miles away from a rocket being lifted off? It's better if you were 300 yards from the rocket, you're going to be blown to smithereens anyway. All right, this rocket is lifting off at, 600 miles per hour. And as you're watching that rocket go up, the angle of elevation between you and the rocket is changing. I want you to find the rate at which the angle of elevation is changing at the instant when the angle is pi over 4 radians. So you remain 3 miles away from the rocket. The rocket blasts off at 600 miles per hour. At some instant, the angle between you and the rocket is pi over 4 radians. I want to see how fast this angle is changing at that instant. So I don't know that I needed a nice 3, 4, 5 triangle because I don't think I have it and I don't care. So there are 2 things changing in this picture, the angle and that vertical distance. So you need 2 variables. One of them I gave you, theta. And then we've got the rocket going up, so let's just call that y. So the 600 miles per hour is not a value of y. The 600 miles per hour is a dy dt. You're looking to find d theta dt at the instant when theta is pi over 4. So now we need some equation that relates theta with y at any time t. The tangent, we've got the opposite and the adjacent sides involved. So we have that the tangent of y is, it's not y, the tangent of theta is y over 3. There's your position equation. Start with it. Take the derivative of both sides with respect to t. The derivative of a tangent is the secant squared. And then you'll have to multiply that by d theta dt. You can think of y over 3 as 1/3 times y. And then you can take the derivative just of 1/3 times the derivative of y. And you'll get something like this. Secant squared of theta, d theta dt, is equal to 1/3, then the derivative of y is dy dt. Is that what you got? I gave you every number except the d theta dt. So we've got secant squared of pi over 4, d theta dt is 1/3 of 600. Let's see, the cosine of pi over 4 is the square root of 2 over 2. The secant squared is 1 over the cosine squared. So the secant of pi over 4 is 2 over the square root of 2. And so the secant squared is 2 over the square root of 2 all squared. Two squared is 4, square root of 2 squared is 2, so that number is just 2 right here. So d theta dt is 200 divided by 2. That'll be 100 radians per hour. Oops, lost it. Was that too easy?
The other things that we had as related rates were areas of objects changing, like the circle, the oil spill, the volume problems. If you get stuck with a volume formula, I'll give it to you. If we're doing the volume of a sphere, I'll give you the 4/3 pi r cubed. We had the Pythagorean theorem problems, like the boat being pulled in, and you want to see how fast the boat's moving towards you when so much rope is left out. Can you think of any others? The cars driving off from each other. So that's another Pythagorean theorem kind of thing.
There's a really fun one. You have to find the shape of someone's shadow, and what you do to their shadow.
Yeah, I didn't think that was so much fun because you didn't have to do anything.
No, they made it really weird. So you have to define the whole base of the triangle by y, when it's x, plus y minus x.
It was wild, crazy, fun, but those two, the derivatives are too easy.
Oh.
Right? Boring. Okay, so practice the related rates problems from that worksheet and from the web work. I just want to do a whole bunch of them here.
In section 3.8, we had two things. We had the differential and the linear approximation. If y is equal to f of x, the differential in y is called dy, and that's just the derivative times the change in x. And we use the differential in the linear approximation. To y at some messy x value was given by the equation of the tangent line. Y is equal to y1 plus f prime at a nice x near the messy x times the change in x, where the change in x is the messy x, minus the nice x. The differential in y is something that is used to approximate an exact change in y. So things that we did like this were by approximately how much will the volume of a cube change if the side is increased from 2 inches to 2.5 inches.
Probably too easy of a problem.
Use dV to approximate exact change in volume.
Because if you were to find the exact change in volume, you'd have to find the volume of the cube when each side was 2.5 inches and subtract the volume of the cube when each side was 2 inches.
So the exact change is not too hard to find.
What's the volume of a cube? Side times side times side. So
We're just approximating 2.5 cubed minus 2 cubed, because the volume is side cubed. So that's not hard to do exactly, but I said don't do that. Find dV to do that. So dV is approximately delta V. dV is the derivative of this with respect to S
times the change in S.
So here, dV is 3S squared times the change in S. So with our numbers, we'd have 3 times the side, pick the nice number here, and then the change in the side, well, it grew by a half an inch. So 4 times 3 is 12, 12 times a half is 6. So the volume increases by about 6 inches cubed if the side is increased by a half an inch. So that's how the dV works. And the other thing that we used was the linear approximation, and that was something like this. Use a linear approximation to estimate (8.2) squared minus 8.2 plus 4.
So in that case, you treat that as a function, x squared minus x plus 4.
And you want to write the equation of the tangent line to that particular
Parabola at the point where x is near 8.2. So we'll write it at x is 8.
So the linear approximation is just the tangent line to this function at the point where x is 8.
So nice nearby number.
So that's kind of a quick problem. You can write the equation of the tangent line to that real quick.
Y prime is just 2x minus 1.
So at x is 8, y prime is 16 minus 1 is 15. And so the equation of the tangent line will be y minus y1 is equal to our m times x minus x1. We need y1, so we need to go back up here and put 8 in. 8 squared minus 8 plus 4. 8 squared is 64. 64 plus 4 is 68. Minus 8 is 60. So that's the y1. And so if I move the y1 over, I have y is equal to 60 plus 15 times x minus 8.
And the very last thing you do is see what the y value is on the tangent line at the messy x of 8.2.
So now let x be 8.2. And you have y is equal to 60 plus 15 times 8.2 minus 8. So 0.2 times 15 is 3. So this number here is roughly equal to 63. Is that too fast? Because I'm getting bored with this review. It's taking too dang long. I still have 2 sections to go. Don't worry, you did one from section 4.1. Find the absolute max and the absolute min of a function on a closed interval. We did that at the beginning of that web work problem. I feel like I've done that one already.
You need the test, right?
Not yet. The test is Tuesday.
I know, but when you do, you know exactly what you're going to be giving us, so you know how to...
Kind of like this is, I'm making a test right now. This is kind of the way I do it. I just go. Sometimes I check my work. No, I don't. I just go. You're kind of lucky you're getting good numbers today. You got to hope that I'm feeling it when I'm making the test, so your numbers are nice. Because look, we got a nice whole number. Look at these numbers, man. It's just awesome.
I will say you're going to have a very fun time grading it if we have some really funky looking answers.
See, I'm always thinking about you when I make out the test. Okay, so on page 9 here, good God, we're on page 9. Section 4.1, find the absolute max and min of a function on a closed interval. Been there, done that. You guys pretty much have that, right? That's a gimme problem. Here's we'll do that problem first on your test. Because everybody's going to get that one right. Correct?
Absolutely.
Good. So I won't work one. Section 4.2, be able to state the mean value theorem and be able to use it. Nope. Yeah. Mean value theorem says that every continuous function defined on the closed interval AB and differentiable function on the open interval AB satisfies that somewhere in there the slope of the tangent line is equal to the slope of the line through the 2 endpoints. So for f continuous on AB, f differentiable means it has a derivative. Then there exists some number c in AB for which the slope of the tangent line, that's a c, is equal to the slope of the line through the 2 endpoints. Okay? So, find such c for f of x is equal to, how about the square root of x squared minus 4 on, well, let's see what this is defined for. I need to have my x bigger than 2. So let's go on the interval from 2 I don't know, let's go 2 to 8. I wonder if I just made a hard problem. Depends on what the derivative looks like. Oh, f of 8's not a very good number. Square root of 60. Yeah, who cares? Numbers. Go with it. Roll with it. Roll with it.
You know what a lesson is?
Yeah, better get done with this. Probably have a 10-minute lesson today. That's x squared minus 4 all to the 1/2 power, so let's go ahead and take the derivative. So f prime is 1/2 x squared minus 4 to the negative 1/2 times 2x. The half and the 2 cancel and leaves me x over the square root of x squared minus 4. So I'm going to put a c value in here. C over the square root of c squared minus 4. Now over here I want f of b, which will be f of 8, minus f of 2 over 8 minus 2. I might have given you something too hard to solve. F of 8 is the square root of 8 squared minus 4. F of 2 is the square root of 2 squared minus 4. 8 minus 2 is 6. So I have c divided by the square root of c squared minus 4. 64 minus 4 gives me the square root of 60. 2 squared minus 4 is 0. So here's what I'm trying to solve for c. Don't know if that's going to be any easy, but we'll try. I'm going to cross multiply, and I will get 6c is equal to the square root of 60 times the square root of c squared minus 4. I'm going to square both sides, and I get 36c squared is equal to 60 times c squared minus 4. Oh, we're rocking and rolling now. 36c squared is equal to 60c squared minus 4 times 6 is 24, 240. So when I move that over here, I get a negative 24c squared. Ha! This is working so well. Dang! Divide both sides by negative 24, and I get c squared as a positive 10. So c is plus or minus the square root of 10. I'm in a positive interval, so c is the square root of 10, is the number guaranteed by our mean value theorem. That worked out real well. I didn't give you time to try it yourself because I was afraid that it wasn't going to work out real well and that you'd all freak out. And then I'd have to do one of these to you. Come back to it, man. Oh, you're probably ready for a test right now.
That's definitely.
So what's the hardest part? What are you going to study for the most?
Yeah.
Yeah? It's a skills thing. All of them need to be done with a little repetition, maybe try 3 or 4 of each type. What I'd ideally like you to do is go through the review sheet. See if you can work those. I always make mistakes on the answers, so if you differ in anything, send me an email and ask me what the heck's going on with this problem. Try it. Maybe if you got time tonight, and then you can come ask me questions tomorrow or Monday. Or you can just email me your questions. Either way. Good? Whew! I feel like I've done a lot. Because I've done 9 freaking pages. If I got paid $1 a page, I'd have $9. That's like nearly a 6-pack of decent beer. Or I could drink the cheap stuff. Life is too short. Just remember that if you learn anything in college, life is too short to drink cheap beer. Tell your mom and dad I taught you that today in calculus.
You say, God, that's my safe word.
Because when I was in graduate school, they literally had generics were the big thing. So they had this beer in white cans, and it said beer. It wasn't beer. They went to a pasture and had some horses pee in a can. But it was like 95 cents a 6-pack. And we were in graduate school and had no money. And that was many, 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 many years ago.
Don't tell your parents I said that. I'm just on tape saying that wasn't me. That was a disgruntled student. I want you to know that the first derivative tells you where a function is increasing or decreasing. The second derivative tells you where a function is concave up or concave down. And those two items together tell you how to graph a function. True? Okay, we're going to try one of those because I have 20 minutes left. And then I'm going to show you something called the second derivative test. All right, so we're going to try to find a piece of paper somewhere. I got two pieces of paper. So this is the new material. It's not on test 2. I am now on page 10. Okay, so this is section 4.3. So intervals on which f prime is positive means f is increasing. Intervals on which f prime is negative means f is decreasing. F prime is equal to 0 at critical points. You can determine whether a critical point is a relative maximum or relative minimum using the first derivative test. So if you have a critical point at x is equal to c, and the sign of f prime going from negative to positive, that means that the direction of f goes from down to up, which says you have a relative min. If it goes the other way, you've got a critical point, and the sign of f prime goes from positive to negative, then the direction of f is up to down, and f of c is a relative max. The next thing we found out was that the second derivative is equal to 0 at places called inflection points. Not only equal to 0, we can also say where f prime does not exist or where f double prime does not exist. Those are called inflection points. Technically, they're not an inflection point unless concavity changes. But if I have an inflection point, I'm going to call it inflection point IP. And I look at the sign of the second derivative. I don't need to do okay, I don't need the number line thing. If the second derivative is greater than 0, that means f is concave up. If the second derivative is less than 0, then the graph is concave down. Yep. So here's our problem. I'm going to let f of x equal x minus 12 to the 4th power minus 2 times x minus 12 cubed. And I want you to tell me, fill in the blanks here. I want you to tell me what the critical points are. I want you to tell me where it's increasing. I want you to tell me where it's decreasing. I want you to give me where the relative max is, where the relative min is. I want you to give me the inflection points. I want you to give me where it's concave up, where it's concave down, and then I want you to graph it. And then I'll move that up so you can all see it. That's what I want you to do. There's our example.
So, all the way down to here. Your first derivative tells you all that information. Your second derivative tells you the rest. So do the first part kind of fast. And then I'll check with you on the first part. And we'll do the second part together, I suppose. Try to factor your derivative instead of multiply it out. Factor it. Polynomial factoring. Right? Your first derivative is just that. 4 times x minus 12 cubed minus 6 times x minus 12 squared. Because the derivative inside is just 1. So there's a common factor of 2 and a common factor of x minus 12 squared. So let's pull out the 2 times x minus 12 squared. And you'll have a 2 times an x minus 12 in here. And then minus 3. Are you with me to that? So let's go ahead and combine terms in here. So I'll have 2x minus 24 minus 3. 2x minus 24 minus 3 gives me 2x minus 27. Are you happy with that? Anybody happy with that? One person is happy with that. What's wrong with the rest of you losers? So we have two critical numbers. X is 12 and 27 over 2. So you're going to put those on the number line. 27 over 2 is 13 and a half. So here's x is 12. Here's x is 27 over 2. And you're looking at the sign of f prime. I'm going to do it in factored form. But notice that the 2 and the x minus 12 squared, God, you can't even read that. Maybe you can read it. 2 times x minus 12 squared is positive, so you don't even have to test anything in there. So just put numbers in here, and the sign of this factor tells you the sign in each interval. And again, 27 halves is 13 and a half. So if I put like a 0 in there, 2 times 0 minus 27 is negative. If I put a 13 in there, 2 times 13 is 26, minus 27 is still negative. And then if I put a 14 in there, 2 times 14 minus 27 is now positive. So we have decreasing, continue to decrease, and then increase. So it only increases from 27 halves on out. It decreases to the left of 12, and then again between 12 and 27 halves. What about the choice of relative maximum? There is none. The graph doesn't turn around the way it needs to have a relative maximum. We do have a relative min. Where? At the 27 halves. Okay, now, I'm going to do the second derivative from here. That looks like a real quick place to take a second derivative from. And we need quick. The second derivative is 12 times x minus 12 squared minus 12 times x minus 12 to the first. So I've got a common factor of 12 times x minus 12. So if I pull that out, I have one more factor of x minus 12 there. If I pull that out, I just have a 1. And so my second derivative looks like 12 times x minus 12 times x minus 13. The second derivative is equal to 0 at the inflection points. So I have an inflection point when x is 12 and another one when x is 13. We need the sign of the second derivative. So we put our inflection points on a number line and analyze the sign of this. So we have a 12 and a 13, and we want the sign of f double prime. So we're just plugging things into here. If I put a 0 in for x, my first factor is negative, my second factor is negative. The product of two negatives makes it positive. If I put a 12.5 in for x, the first factor is positive, the second factor is negative. Positive times negative is negative. And then if 15 is in there for x, both are positive, so my sign is positive. And remember, that tells us about the concavity of f. F is concave up in these two intervals, concave down in between. So I write that it's concave up to the left of 12, and then again to the right of 13. But it's briefly concave down between 12 and 13. So we're going to put that together in a graph. We need to plot the critical number at least. Two critical points. Here, I'll help you. F of 12 is 0. Your turn. That one's not 0. F of 13 halves, 13.5, 1.5 to the fourth, 1.5 cubed, blah, blah. I don't care what that number is. It's not worth it. It's a minimum somewhere. I don't even care if it's positive or negative. But I know that at 12, the graph goes through 0. And if it has to, according to this information up here, drop, continue to drop, let's put 13 halves here. That's going to be some negative number. And then it's got to climb. That's what this part tells us. Drop, drop, climb. But it's got to drop in such a way that it's concave upward here between 12 and 13. So let's put 13 right here. It has to be concave downward. And then past this point, it has to be concave upward. And remember, at 12, we had 0 slope. So it's going to come down here in a concave way in such a manner that it looks like we're going to have 0 slope at 12. So something like that. But follow the dotted line now. Make your graph continue to decrease and be concave downward. So that little portion right here has to bow a little bit concave downward. I'll try to exaggerate it enough so that you can tell. Here on out, the graph has to be concave upward, but follow the dotted lines. So concave up, concave up. So the first derivative just told you it looked kind of like a parabola, but the second derivative tells you somebody put a punch in that parabola right here and knocked it in a bit. Okay? So we're going to need practice graphing things. There's a whole section beyond this where we graph things with more complicated features, like where those sharp corners appear, or where vertical and horizontal asymptotes appear. So we'll spend a lot of time graphing using this. One byproduct of the second derivative telling us about concavity is that we can also use the second derivative to tell us about relative extreme values. It's called the second derivative test. And let me tell you what it is. Now we know that if a function has a relative max or min, it's going to occur at a critical number. A critical number is a value of x where the first derivative is 0, or where the first derivative fails to exist. So this refers to critical numbers. Let's let x is equal to c be a critical number. For y is equal to f of x. In other words, f prime of c is 0, or f prime at c does not exist. Instead of drawing a number line and looking at the sign of f prime, we can look at the sign of f double prime at the particular critical number. We calculate the second derivative. We take our critical number and plug it in. We find out our second derivative at the critical number is positive. A positive second derivative indicates the graph is concave up. So that means our critical number has to be a min. If we plug our critical number in the second derivative and get a negative value, that means our graph is concave down, and our critical number has to be a max. So we plug that in. If f double prime at c is positive, then f of c is, that's the concave up case, a relative min. If f double prime at c is negative, then f of c is a relative max. If f of c is equal to 0, we've got to go back and use the first derivative test. F double prime at c is 0, test fails. Go back and do the whole thing with the number line. And so I'll do an example of this the next time, a week from today. But there's some things like that on your web work, so when you're doing web work, you might look at that.
Before anyone runs away, I made a group meet. If anyone's interested in joining, I have the link here. I thought it was about time that we had a group meet. Could you put this up? Yeah.
I'll put it here.
Oh, that's great.
Just let it go for a minute. It'll come back.
Cool.
What's a group meeting? That sounds kinky. Oh, that's group me, not grope me. Sorry.
It was still recording!
When will I ever learn?
Please tell me you're going to post this unedited on the
I don't,
website.
you know.